All right. Hey there, everybody. So the problem we're considering is by now familiar in this upper box here. So this is first-time fraud, so it has to be unsupervised. Other constraints are that it's big data, so the resulting method has to be efficient. These other two, I think, are kind of important and really led to this work. So the end of the chain here, we focus a lot on the fact that in reality, in a bank or whatever, there's actually going to be a human analyst who is going to actually sort through all kinds of transactions. And so we as the machine learning people, whatever, normally focus on what happens in training and so on, but this is really focused on what happens at testing time in a way. So we're going to have a whole bunch of incoming transactions, and they're going to make some model. You normally give it some anomaly score for each test point. But we're focusing on this next thing, which is that you're going to somehow, first of all, prioritize those. Even though you have some anomaly scores, there's one other thing you probably want, we argue, which is a calibrated score, which you can. One good way to do that is by quantiles. It gives you at least some relative sense of how important each test point is. You get then some smaller inspection set this poor human is going to have to go through, and a picture. So I think the picture is really quite important for understanding what's going on. That person is going to, every day for hours, stare at a whole bunch of transactions, figure out, is this really something we should look more into or not? Okay, so we build upon an approach which I did a while back as a professor. And back in academia, you like a nice, more beautiful things which tend to be continuous. And sort of out in an ugly sort of industry land, a lot of things are discrete, which just makes things a little more difficult, it turns out. And so this is sort of a version, in a way, of a method we presented at KDD, where we really try to grapple with discrete and continuous mix, which turns out, as simple as that sounds, as many of you, it was mentioned in at least one talk, discretization and mixing, you go from a mathematical PDFs, you have to go to PMFs, probability mass functions, and figure out what happens when you mix them. So, but the basic idea is you have an unsupervised decision tree, which maybe you're scratching your head. What is that? Wait a minute. Decision tree should be supervised. It turns out there is a way to do an unsupervised decision tree. And basically, I'll show you the picture. This little math, if you're interested, shows exactly that it really is like a decision tree. And you end up with this picture, and then you can read off things from root to leaf as rules, as shown here in this example. And in a leaf is essentially a density, or in this case, a probability mass function. And that one turns out to be an outlier. Here's a little evaluation on some real, the best public data, at least we could find, of this kind. And you get these benefits using the decision tree framework that we're all familiar with, except that it's unsupervised. It has all the interpretability of a decision tree, can handle mixed data, has the speed advantages of decision trees, but a few more things. It has true probabilistic semantics. You can actually compute these quantiles in closed form, and that gives you a calibration. Naturally handles missing values without any artificial external data processing, similar with feature selection. This is somehow an unsupervised method that does feature selection. It's maybe a little unfamiliar, and it can actually compute feature importances, which are good for interpretability as well, the same way you can get out of random forests and so on, and very easy to implement. So these are all, we find, very important things in practice. So if you want to find out more, or if you want a job, you should come talk to me. And if you want to find out more about how the discretization works, also talk to me. Thanks.